My name is Natasha Bieto, and I am presenting today on the effects of Hurricane Katrina and the land loss that it caused. If there were ever a competition for the most catastrophic hurricane in the history of Louisiana, Hurricane Katrina would undoubtedly take the crown, particularly regarding the extensive damage inflicted on people, homes, and the environment. This storm caused an astonishing $108 billion in damages and resulted in nearly 2,000 lives lost. The environmental repercussions for Louisiana were equally as devastating, leading to significant land loss and presenting engineering challenges. On August 29th, 2025, Hurricane Katrina made landfall on Louisiana's Gulf Coast as a Category 4 hurricane. The storm unleashed exceptionally large storm surges, surpassing 27 feet in several regions, compounded by levee failures, floodwaters, and over 8 inches of rainfall, along with triggering numerous tornadoes across the southeastern Gulf Coast. Although Louisiana is no stranger to hurricanes, Katrina was the relentless force that held New Orleans underwater, literally. Since 1932, the Louisiana coast has faced considerable erosion, losing 25 to 35 square miles of land annually in an area larger than Manhattan, due to a combination of subsidence and global sea level rising. Storm surges have worsened this predicament, pushing water towards the shore and accelerating subsidence. The hydrometeorology of Hurricane Katrina is fascinating and warrants further examination, particularly from an engineering and conservative perspective. This exploration will delve into the excess water from Hurricane Katrina, exacerbated by already severe land loss in Louisiana, with a small focus on engineering implications. The development of a hurricane requires 4 essential components to ignite its energy. A pre-existing weather event, Hurricane Katrina began as a tropical wave, combined with remnants of another tropical depression, turning westward towards Florida on August 25th. Tropical Depression 12 formed on August 23rd, 2025, and became Katrina on the 24th. While over the Bahamas, it was the 11th tropical storm of the 2005 hurricane season. Katrina intensified before making landfall in Florida, becoming a hurricane approximately 2 hours prior to impacting the southern east coast of the state. Near the border of Miami-Dade and Broward counties, a well-defined eye was visible on the radar imagery throughout its journey across Florida. Katrina spent around 6 hours over land before re-entering the Gulf of Mexico early on August 26th. In the Gulf Coast of Mexico, Hurricane Katrina underwent 2 phases of rapid intensification from the 26th to the 28th. These changes occurred swiftly, driven by environmental factors, including low wind shear, the path over warm waters, and repeated exposure to the same current. These conditions allowed for Hurricane Katrina to reach Category 3 status by the 27th, developing a clear eye and expanding its wind field. By August 28th, it dramatically escalated from a Category 3 to a Category 5 hurricane with within a mere 2 days, with peak winds reaching 278 kilometers per hour or 172 miles per hour. On August 29th, Katrina changed direction toward Louisiana as the atmospheric ridge that had been directing it westward shifted east. Although it weakened, it remained a massive storm when it made landfall over Buras, Louisiana. At this time, it was downgraded to a Category 3 hurricane, but still had impressive winds at 204 kilometers per hour or 127 miles per hour. Its second landfall occurred over the mouth of the Pearl River, leading to further weakening. By 1 p.m. on August 29th, Katrina had diminished to a Category 1 hurricane and was classified as a tropical storm. The wind speeds were less intense than predicted due to low pressure and landfall and wind expansion upon reaching land. The geographical impact of Katrina was profound, with its most destructive effects stemming from the storm surge and subsequent flooding caused by levee failures. While the focus is primarily on Louisiana, it is important to note that Mississippi experienced devastating storm surge of up to 28 feet along a 20-mile stretch of beach. In Louisiana, particularly New Orleans, Lake Pontchartrain flooded due to heavy rains, with waters reaching as high as 19 feet. The winds from Hurricane Katrina pushed water levels so high that it surged back up the Pearl River, resulting in significant flooding and further eroding already disappearing land. The land loss caused by Katrina is illustrated in the figure below from Live Science. These elements work together to fuel a hurricane. It is typically originated in warm tropical waters as a tropical wave, which is a low-pressure system traveling through moisture-rich areas, enhancing shower and thunderstorm activities. This system continues westward into zones of warm moisture where warm air rises, creating additional low-pressure systems that draw in even more warm air. As this air rises, it cools, droplets are released, further intensifying the storm. When wind speeds reach at least 74 miles per hour, it is classified as a hurricane. Therefore, the necessary conditions include a tropical wave, water temperatures of at least 26 degrees Celsius at a depth of 50 meters, thunderstorms, and wind speeds of 74 miles per hour or more. Louisiana's landscape weakened even further after both Katrina and Rita, with more than 500 kilometers of wetlands being washed away. These wetlands are especially vulnerable because of weak soils and shallow plant roots found from studies of areas of low salinity versus high salinity. Freshwater areas proved far less stable than saltier marshes, which had deeper, stronger roots. Data from the study mentioned above suggests that freshwater restoration efforts may unintentionally weaken the land, leaving it open to erosion during major storms. Field measurements also from the salinity studies showed that low salinity wetlands contained a weaker layer beneath the surface, which much lower strength than saltier soils. Laboratory tests confirmed that this weak zone could not withstand the wave stress produced by Katrina, while stronger high salinity marshes endured. Simulations demonstrated that repeated waves would continue to wear down these weaker layers. The study concludes that freshwater diversions, though well intended, may create wetlands more likely to fail in future hurricanes if the soil remains weak. At the present time, there has been a new committee convened with the task of mitigating the disaster and land loss due to hurricanes combined with the effects of flood relief as well. This came to light after the horrible failure of the levees during Katrina and an outcry that the Corps of Engineers' strategies were outdated and ineffective. Following Katrina and shortly after Rita, Louisiana established the Coastal Protection and Restoration Authority. This agency created a master plan to focus on restoring the barrier islands of the state. In addition, there are plans for marsh creation and sediment freshwater diversions. The biggest project going at the present time is dredging sediment, building land, and planting new marsh grasses so that those newly built up area will thrive and grow further. The organization is at present accepting new ideas to put into motion for preservation efforts. As you can see from detrimental reshaping of the Louisiana coastline by Hurricane Katrina, many lessons can be learned. There is an urgent outcry for engineering and conservation strategies due to these extreme hurricane impacts. The unparalleled destruction called for implementing comprehensive master plans and are refocused every 7 years to restore the barrier islands, create new marshes, and develop sediment and freshwater diversions. This ongoing work by the CPRA in Louisiana leans toward a positive disaster mitigation and potential new headway in storm mitigation and remediation for furthering Louisiana's future.